Yeah, that's a Friday. And let's see what we're gonna do today. We were doing some intuitive talk about limits before I start. Anything that you want to ask about anything going on with your web work or anything else in your lives? Okay, if anybody needed it. Okay, so in sections 2.1 and 2.2, I'm going to kind of put them together today. We'll talk about limits. Limit's a y value on some graph near, if we write something like this, a limit of some function f of x as x approaches some number on the x-axis, call it a, is a y value L if that any epsilon greater than 0, there exists some positive number delta with the distance between F and L is smaller than that number epsilon whenever x minus a is smaller than some number delta. Does that look like gobbledygook? It says, you tell me whatever tolerance that you need. That's this number here. How close? I want these numbers to be within 1/1,000,000 of each other's value. Okay, then my job is to find an interval around A, when I plot those numbers into F, I get F and L within 1/1,000,000 of each other. So I can make these two y values close. So geometrically, whether or not there's a point on the graph when x is A, if I'm in some sort of small interval around A that has some sort of width of delta, then all my y values for F in that interval, whether or not there's a y value there, who cares, can be made infinitely close to that number L. So that interval there is what I'm calling the epsilon interval. Now, there could be a point there. There could be a point elsewhere, maybe here. But I'm looking at the y values near x is equal to A. And so I was going to do one intuitively with you by plotting points. And the one we started last time was the one that looked like x cubed minus 1 over x minus 1 does not have an actual y value on the graph when x is 1. Because when I try to plug 1 in for x, I get 0 on top and 0 on the bottom. So there's not a point there at all, but I want to see if there are points near, maybe some missing place right there. And so I want to look at what happens when x is a number near 1, but not exactly equal to 1. So I'm going to just make a table of values. I'm going to pick numbers first that are smaller than 1 and go toward 1 from the left. Not terribly legible. Let's move this thing over. That's not going to work right there. Okay. Good. Can you limbo? Okay, still low. Let me get it higher. Up. Better, no better. Okay, so I plotted some of these, and I did them when I had a calculator. I did want to tell you about this. Texas Tech in the SOAR office offers supplemental instruction for several classes, but they do have supplemental instruction for this class. Calculus 1, every Tuesday and Thursday. Supplemental instruction. Called SI. These are peer-led review sessions. This particular student has to attend somebody's calculus class, and then during the week, he'll get up and review what was done in that calculus class. So right now, we're all about the same, but after a while, our class will get ahead of everybody else's because you're just so smart. But I think it's a good idea if you ever need to get caught up in anything. They are Tuesdays and Thursdays. 6:15 to 7:45. It's in the MCOM building. That's that one up there. Room 55. Every now and then they change the time, but I think they're going to try to stick with this. The person who is the SI leader is a person named Jose. You can come and go, just not be disruptive or anything, but if you've got particular things that you're stuck on and you want to go and see if they're doing any additional problems on that, a lot of times these SI leaders have some worksheets that they go through. I really think you should attend just because you guys are prime candidates to be the SI leaders next semester. So you might see how it's run, and if you like doing it, and then if you feel up to it, apply for this kind of job and get that minimum wage to work calculus. We also have free tutoring in the math department in room 106, I believe it is. If you're ever in the math department on the first floor, if you enter the building through the main entrance and turn to the right, you'll see a Coke machine. By that Coke machine, there's an open area, a classroom, an X classroom. That's now kind of a study hall with long desks in it. And some of our graduate students work there. And you can go in there at any time if you want just a quiet place to do homework. They have the little whiteboards on the desk where you can scribble on the desk, and if you get stuck with something, you can raise your hand and somebody will answer your questions. So in Math 106, every day has free tutoring. I think it's like 9 to 5, but I'm not sure, but I'll just say it like I am sure. Good place to go if you're wandering campus and don't want to be around people, and just kind of tuck in there and do your homework. Okay, so I said I was going to plot some points. I'm looking at y values slightly smaller than 1. So I'm going to plot x is 9/10. So I take 9/10 and I cube it, subtract 1, divide by 9/10 minus 1. When I did that, I get 2.71. I did that manually the other day. Now I'm going to get closer, so I'm going to put another 9 behind the decimal. So I'm at 99/100ths. And when I plug that in, cubits, subtract 1, divide by 0.99 minus 1, I'm going to get 2.9701. So I go again, I stick another 9 behind that other one, and I get 2.997, and then 001. And so what the heck, I got room for one more. So 9,999 over 10,000. And I get 3 9s behind the decimal, and then the 7, and then I think I get 4 zeros and then the 1. So these are nice, pretty symmetric numbers. Oops, I think I just get 3 zeros behind the 1. But you can almost guess at what the next one would be if I stuck another 9 back there and another 9 and another 9. I can make those, I can just keep making these numbers closer and closer and closer to 3. I may never hit 3, but I'm going to have so many 9s behind this decimal by picking more 9s behind the decimal there that I can make this really doggone close to 3. Right? So I'm going to say, as I go from the left of 1, these y values are going toward 3. Now, what I need this to do is there not to be a jump in the graph. I've got to have this hook up. So now I'm going to pick numbers slightly bigger than 1 and plug them in and see if they meet at 3 or if they miss. If they miss, then there's no limit. Limit has to be in a certain interval. All the y values are the same. So I'm going to come and continue my table, pick numbers a little bit bigger than 1, and then squeeze them closer and closer to 1. So I'm going to start with 1.1 and plug that one in. I think I started with 1.1, and I get 3.31. And then I put a 0 behind the decimal and then the 1, and I get 3.0301. And then another one, put 2 zeros and then the 1 behind the decimal. And you get 2 zeros and then the 3 behind the decimal. And then some other stuff. But kind of the same symmetry type thing is happening again. The next one you can predict is going to have 3 zeros before I hit the 3 behind the decimal. So again, I can keep doing this just by putting more zeros behind that decimal. I can make these numbers squeeze toward 3. And so we'll say that limit is going to be 3. We'll talk about some algebra that'll get us to that same spot, but let me show you a function where we have no algebra to get us to a particular limit. Let's look at taking the limit as x goes to 0 to another fraction that doesn't exist when x is 0. Sine at x is 0 is 0. And then the bottom is 0. So again, it has that indeterminate form where there's not a point at x is 0. So again, not defined when x is 0. X equals 0 gives another of our indeterminate forms. So we're going to make another table of values and pick numbers from the left and the right and see if these squeeze into a particular value or if they miss. If they squeeze into the particular value, we say it's the limit. If they miss, then we just say this function has no limit as x goes to 0. I did all this calculation in radian measures. So if you're following along or need to try it at home, we're going to do it in radians. We're going to pick numbers to the left and to the right of 0, but I'm going to save some time. The sine function is an odd function. Remember what the graph of the sine of x looks like? It looks like this right here. and then again over here. So if I pick a particular value here, I'll get a number. If I pick the opposite of its value here, I get the same number. It's symmetric through the origin. The sine of minus x is the same as minus the sine of x. So for instance, if I take as one of my points to plug in a 0.9, I'm going to get a number out of the sine of 0.9. But then on the bottom, I would have my 0.9. Now, if I plug in a negative 0.9, the numerator would just be opposite in sign, and the denominator would be opposite in sign. And so they'd cancel. So in other words, whatever happens at 0.9 is the exact thing for that ratio at negative 0.9. So I don't need to come in from the left and the right with individual tables. I can just do it with positive numbers and agree that the negative over the negative would give me the same positive again. All about saving me some time here. So I'm just going to do these. Let's see, I'm gonna plug them into here in radian measure. And I plugged in, I'm getting numbers near 0. So I just took some positive numbers. If I can fit that in here. So at 0.1, the value was 0.998, 2 3s, and then a 4. And then some other junk behind it, but look, I ran out of room in my box. The next one, I get 4 9s behind the decimal. And then an 83. And then the next one, I get 2 4 6 9s behind the decimal. And then the 83. That's enough to convince me that I'm just going to double the number of 9s behind the decimal just by sticking another 0 behind the decimal there. So I can make that number real doggone close to 1 fast. So, and if I put a minus here, these will all be positive as well because I have a minus over a minus. So this tells me that these numbers are approaching 1. That's going to be one of our special limits. We're going to have to just agree with that one. There's not many algebra we can do to compute that. But here, we will be able to do some algebra. Does anybody have any ideas what kind of algebra we can do to this thing? No? Pretty good factoring? Yeah, you can factor x squared minus 1, but I don't know about x cubed minus 1. But it does mean there's a common factor in here. Just don't know what the other factor is. So how do we just divide and see what the common factor is? What do I multiply x minus 1 by to get x cubed minus 1? So let me remind you how to do long division with polynomials. Let's take x minus 1 and divide it into x cubed minus 1. So I'm going to write it like this, x cubed, and then plus 0x squared plus 0x minus 1. I know it divides evenly because it behaves like 0 over 0. So now I look at what I multiply x by to get an x cubed. And so I need an x squared. And now multiply both of those terms by x squared. And then just like with a regular long division, you subtract that line from the line above it. So you're visualizing that we have a 0x squared up here. So 0x squared minus a negative x squared gives me an x squared. And then this minus 1 from over here. So I do it again. I divide x into x squared. I need a factor of x to get me there. X times x gives me the x squared. X times the minus 1 gives me a minus x. subtract that line from the line above it. The line above it has a 0x here. And when I subtract the negative, I get a positive x, and then the 1 from over there. Now I can see that if I multiply that by 1, I get x minus 1. And so I get 0. So what that's telling me is that that x cubed minus 1 factors as x minus 1 times that guy. And so when I divide this by x minus 1, I'm dividing that by x minus 1. And as long as x is away from 1, I can cancel that factor. Well, in a limit, x is away from 1. So what I'm doing next is I'm taking the limit as x goes to 1 after I've canceled the x minus 1s of this. Now that's just some sort of parabola, right? That's a polynomial, so it's like a parabola. There's no holes, jumps, or breaks in it. It has an actual y value when x is equal to 1. What is that y value when x is equal to 1? 1 here and here. Okay. And you get 3. That's typically the way we're going to try to compute limits. If we have an expression that is 0 over 0 at that particular value of a, we're going to try to rewrite an equivalent expression that looks like the same function near a. If that equivalent expression has a limit when x is a, we can just plug that number in and get a number back out, then that number is going to be the limit. Anybody remember long division? Does anybody remember synthetic division? Let's do the same division using synthetic division. Let me show you how to do that. If you divide a polynomial by, say, x minus a, then that means x is equal to a is a 0. So when I'm dividing by x minus 1, I put the 1 here. X is equal to 1 is a 0. Then I draw my dividing box upside down. I'm going to leave 1 row here. And in the top row, I'm going to put coefficients of the polynomial I'm dividing into. I'm going to have a 1x cubed plus 0x squared plus 0x, and then the minus 1 on the end. So I'm going to remind you, I've got to have a row for every descending power of x. Now, in synthetic division, the first thing we do is bring this lead coefficient down. And now I'm going to multiply and add, multiply and add. So 1 times 1 gives me a 1, and now I add these two numbers, and I get another 1. 1 times 1 is 1, add these two to get another 1, and then 1 times 1 is 1, add there and get a 0. This 0 is the remainder. A remainder of 0 means I have a factor of x minus 1. And these numbers are coefficients of a polynomial 1 degree less. That's where the 1x squared plus 1x plus 1 comes in. And so that gives me my two factors. And that'll take you right to there. And then when we do the limit, we just see if we can plug that number in, get a number back out, then that's our limit. What this tells me geometrically is that the graph of this ratio follows the graph of the parabola. Now, some parabola opening upward. But when x is 1, there's a hole missing. And the hole occurs when y is equal to 3. So a 0 over 0 typically means something like that. Now, what I wanted to do with the paper that I sent you through email was show you these limits geometrically on a graph. So I sent you something that looked like that. I'm going to try to reproduce this picture. keep that there. Come back to it. Well, I'll just put it up when I need it. I'll remember it. All right, so let's see. I've got my x-axis going from -2 to 4. And my y-axis from -3 to 3. 1, 2, 3, 4. 1, -2. All right, so let's see. I've got a line that goes, looks like from 1, 1 to 0, 0. All the way forever. Then, well, there's a little tiny star about halfway in between here. So let's make that a point. And then it looks like at 2, 2, I do that. And then I go down to 3, 0. That's about right there. So that's something like that. Missed it. Well, close enough. And then it shoots back up. Looks like at about 4, 1. Close enough? Now I'm going to tell you what these things mean. This function has as its name y is equal to f of x. So here's the x-axis. Here's the f of x-axis, the y values. And I want you to tell me this limit, and then let me put another one here. When I was plotting points and I chose numbers slightly to the left of that particular point here, we're doing this limit from the left. The minus sign means x goes to 2 from the left. And here, when I'm plotting numbers bigger than 1 and sliding toward 1, then I'm going from the right. So this says x goes to 2 from the right. So what I want you to do is take your hand and cover up your graph showing only everything to the right of 2. So here's 2, and I only want to look at this part. And so as x goes to 2 from the right, my path is along this part of the curve. And when I'm close to 2, I'm going to see what this y value is right here. Get out of the way, paper. I'm going to look at your paper. What does it look like it might be? You were to find what y value is here. Looks like about 1.5, doesn't it? So let's just agree that that's what it's going to be. From the right, I'm coming in this way, and I'm going across here to about 1.5. Now do it the other way. We're coming in from the left, so cover up everything on the right-hand side of 2. Get close to 2. I'm up here, and now keep sliding my finger down the graph until I'm real close to 2. And now I'm going to look at that y value, and it looks about the same place. If I can slide the 2 points into the same place, then that's going to be the value of the limit. So let me write that down here. For the limit as x goes to a of f of x to equal to L, we require that the limit as x goes to a from the left is that number L, and the limit as x goes to a from the right to be that number L. If we get two different numbers coming in from the left and the right, then we say the limit does not exist. So in this particular example, when I go down to number 3, oops, why did I put a 2? Oh, well, that's not what your number 1 and 2 say, are they? Oh, well, let's make this 1 star and 2 star. I just made my own problems. Or problem -1 and -2, I don't know. But anyway, from this, my little 3 star would say that the limit as x goes to 2, without any implication on the direction of f of x, will also be 1.5. Now let's do the ones on the paper. This number 1 says the limit as x goes to 1 from the right. Okay, so now you're looking at the right-hand side of 1. Cover up everything on the left-hand side. And then squeeze x's in here, and as you do that, follow the graph. So as I'm getting closer, I'm following this path until I'm about right here. So do you agree that that limit, as I come in from the right, is going to be 2? What do you think happens as we come in from the left? X goes to 1 from the left. See what that's going to be. Looks like it's going to be 1, doesn't it? As you're coming in from the left, you're coming up this part of the graph. And so you're approaching this point here. Automatically, I can state that the limit as x goes to 1, without any regard to direction, doesn't exist. So I'm just going to write does not exist, because these two do not meet up. Okay? Any questions? All right, let's look at 4, 5, and 6. We're going to do the same thing around 3. 3 from the right, left, and then make the decision as x goes to 3. So what is your description of the behavior of f when x is slightly to the right of 3? What's the y value doing?
1.1.
Slightly to the right of 3. So I'm covering that up. Like 0, right? Sitting right there on the x-axis. What about if you come in from the left of 3? And you're coming down that parabola, you're going to head toward that same spot on the x-axis, right? And since those match, that's an automatic. Okay. So now to find values of the function, these are the actual points on there. So let's go with number 6 first. Number 6, can you take the limit as x goes to 3? Come in from the left and right, and do they meet up, and where, if they do meet up? Well, we did that one. That is number 6. I'm not on drugs or anything. That's number 6. All right, number 7 then. Number 7 is not a limit. Number 7 says, what is the y value on the graph when x is 1? What is the actual y value there? That's that little point that I put floating around here. It's that little teeny tiny speck on your paper. Right? That's at 1.5. The value of the function doesn't necessarily have to be the value of the limit. And what about f of 3? What's the actual value on the graphs when x is equal to 3? 0. If you look at this graph, there is a place that makes a jump right here. And that's going to be called a discontinuity. That's an example of a jump discontinuity. A discontinuity is going to occur when you have no limit. The left and the right meet at different places. There might be a value of the function there, but there is no limit. Now, if I just remove a single point, that's also a discontinuity. I'll have a limit there, but not a y value. Or if I put the y value, say, down here, I have a limit and a y value, and they're not the same. If that happens, then that's the description of a point discontinuity. If by chance we have a vertical asymptote somewhere, like we do with the tangent function at pi halves, then that type of discontinuity is just going to be called non-removable. It's got a big old rip in the graph, or an asymptote. We'll talk about discontinuities and continuities in section 3, but it has something to do with limits. Now, we are not always going to know what the graph looks like, so let's just try to figure out some ways to compute limits without having to have a graph or a calculator and plot points little by little. We want to be able to do this a little bit more analytically. So I'll give you some limit theorems first. If you have a function that isn't one of these weirdos, a function that doesn't have any breaks, jumps, or holes in it, and you want to know the limit of that function at a particular point, well, then it's going to be the same as the y value. Only times the limit's going to do something weird is when there's a hole or a jump. If there's an actual y value there, it's just the value of the function at that point. Okay, so if you've got a function that's not unusual, none of that showed up there, did it? What can I see? Graph. Oh, well, the graph was on the handout. That don't matter. That's the biggie. It's just not like. There we go. I'll just try to write right there. All right, so I'm going to put the limit theorems right there. Eraser. Okay, so we're looking to compute let's just say if f is nice, something we recognize, a line, a parabola, one of our trig functions, and it's defined at x is equal to a, then the value of the limit is just f of a. But if our expression, if at x is equal to a, we have the form 0 divided by 0, then we must do more. I'm going to try to find an equivalent expression and maybe reduce our given expression to that. With the properties that get them right. Maybe they're not worth writing, but we're going to write them. All right. Suppose my function is just a constant. What kind of graph is the graph y is equal to a number? Y is equal to 5. What does that look like? Horizontal line, right? So that's nice. There aren't any jumps, breaks, or holes in it. So no matter which x I look at, all the y values are at that number. So this says the limit as x goes to a of any constant is whatever that constant is. That's the same c. It didn't mean for it to shrink so drastically. Here's another one of your favorite graphs. The line y is equal to x. That again has no breaks, jumps, or holes in it. What's the y value on that line? Y is equal to x when x is equal to a. It's also a, right? Y is x. So if x is a, so is y. That's essentially, if you can plug the number in and get a number back out, then that's your limit. So if we have any kind of linear function, just plug that number in. Plug a number in and get a number back out, then that's your limit. The next one says, let's see where I can take this. Go to the left. Suppose I have a bunch of terms added together like I did with the x squared plus x plus 1. I'll just write it as 2 terms. Suppose I have 2 things added together. To do a limit of a sum, I can write that as the sum of the limits. In other words, we can do limits term by term. I can do the same with products, term by term in a product. I can take the limit of the first factor and multiply it with the limit of the second factor. We can do that with quotients, as long as the denominator is not 0. Is 0, then something else. If we have some big old messy rule around the function, maybe a power or a square root sign or something. Say I have some function, and if it's under a square root sign, or it's raised to some sort of power, and a square root sign is a power, right? I can go inside the rules. And then apply the power. So here's what I mean by that. Suppose I want to say, take the limit as x goes to 2 of 5x plus 11. That's this guy. Y is equal to mx plus b. So if I take that limit as x goes to 2, I should get 5 times 2 plus 11. 10 plus 11 is 21. If I say this, then that square root sign is really not in my way. I go inside, do that same calculation, and just put the square root sign on the end. That's what that's saying. So we can do limits term by term by term. I can say that this holds no matter what power's on that x, as long as I'm obeying the laws of algebra. All right, so what we're going to do is look at the do more. In our example with the x cubed minus 1 over x minus 1, what we tried to do was find where that common factor was and cancel it. If we can rewrite our original expression in terms of an equivalent expression, maybe different at x is equal to a, but equivalent everywhere else, then we take the limit of that equivalent reduced expression. We're going to look at manipulating the expressions algebraically, the do more steps. And I think that might be where we pick up on number 9. You guys got a number 9 on that handout I gave you? Back to our examples. Problem number 9 says we're going to take the limit as x goes to 0. On top, we're going to have x squared minus x minus 2. On the bottom, x plus 2. So we're kind of looking here. I got a fraction in there. I want to know what happens to x squared minus x minus 2 when x goes to 0. So you try putting a 0 in there. 0 squared minus 0 minus 2, gives me 2, right? Negative 2. On the bottom, x is going to 0, goes to positive 2. So I get a negative 2 over a positive 2. That reduces to negative 1. That's my limit. So our first agreement is when you're taking a limit, if you can plug this number in and get a number back out, that's your limit. That's what we mean by nice. It's a nice function. This function's nice in a neighborhood around x is 0. It's not nice when x is negative 2, because it gives me 0 on the bottom. That's a bad thing in algebra. So that's what I asked for next. What happens if we take the limit as x goes to 2? Now I made that an x minus 2 down there, so let's change that. We do. When x is 2, the bottom is 0. But notice that when x is 2, the top is 0 as well. That's our indicator to do more. That's our indicator that that numerator has a factor of x minus 2 hidden in it. Let's find where it is. If x minus 2 is a factor, what's the other factor? Can you factor x squared minus x minus 2? What's the other factor? Factors of 2, opposite in sign, that add to negative 1.
1.
That has to be a 1, right? Opposite in sign needs to be a positive 1. You check, that gives you a minus 2x as one of the middle terms. A positive 1x is the other middle term, and that does add to that. So it factors. So as long as x is away from 2, I can do this. And we are away from 2 when we're doing a limit. We're near 2. Now I get an equivalent expression. I take the limit as x goes to 2. And I get 3. That's our limit. Okay? Factor and cancel, that's what we're going to try to do. This way. If the factoring is a little bit more difficult, then try synthetic division. But synthetic division only works if you have a first degree factor down here. Otherwise, you can try the long division. How many of you have done some calculus before? I say L'Hopital's rule, does that ring a bell? We're going to do that way in chapter 5, 4, somewhere later in the text, where there's a real quick way to do these limits where you just skip all the algebra stuff. Well, we're not going to skip the algebra stuff because I have ways of finding things in which L'Hopital's rule doesn't apply. So don't just apply L'Hopital's rule here. All right, so I picked one that's harder to factor. We've got the limit as x goes to 1. What is that, an x to the 6 minus 1? And an x squared minus 1. So we try plugging the number in and see if we get a number back out. But in either case, if x is 1, the numerator and the denominator are both 0. We're going to tell ourselves that we checked that, and we found that we got 0 divided by 0. That means do more. I know how to factor x squared minus 1. That's the difference of squares. X minus 1, x plus 1. Can you factor x to the 6th minus 1? Anybody? We don't need to know how to factor because we have synthetic division. Our guess, since the denominator is 0, is that we've got a factor of x minus 1 hiding in x to the 6th minus 1. So we're going to guess that. We're going to find the other factor either with long division or synthetic division. We're going to divide by x minus 1 to see what the other factor is. I can divide by x squared minus 1, but not with synthetic division. I'm going to divide by x minus 1. So we're either going to do this, or we're going to put the 1 out here, 1x to the 6th, 0x to the 5th, 0x to the 4th, 0x to the 3rd, 0x squared, 0x, and now the minus 1. All lined up. I'm gonna let you try it, see if you can figure out what the terms are that go in there. Bring this down, multiply and add. Bring that down, multiply and add. Keep going like that. Let's see if you can find the other factor. And if this is a factor, then we should get a 0 right here. It's supposed to be quick. Got it yet? All right, the one I brought down, 1 times 1 is 1, 1 plus 0 is 1. 1 times 1 is 1. I'm gonna get a bunch of ones here, aren't I? So that looks like, as the other factor, 1x to the 5th plus 1x to the 4th plus 1x cubed plus 1x squared plus 1x plus 1. And now cancel the common factor. And we take the limit with what's left. X to the 5th plus x to the 4th plus x cubed plus x squared plus x plus 1. And I still have an x plus 1 on the bottom. So what do you get? I'm not gonna get 0 on top because I'm adding a bunch of 1s. X is going to positive 1. I'm gonna have 1, 2, 3, 4, 5, 6 over 2. So my limit is 3. Factoring and canceling is one of the things we're going to look to do. Number 12, what time is it? 15 minutes-ish. Doing good? Am I still awake? Right. Right here. This is problem number 12. I lost a space in number 11 and 12. We're looking for the limit as x goes to 0. We have 2 times the quantity x minus 3 squared minus 18, all divided by x. So what's happening to this expression when x is equal to 0? 0 there. I get a -3 in the parentheses. -3 squared is 9. 2 times 9 is 18. Minus 18 is 0. Show that. Put a 0 for x on the bottom, and I get 0. You got to do some more. And this one's telling you what to do. Multiply it out. Spread this all out and see what happens. Take x minus 3 and square it. Then send the 2 through there. Then subtract 18 and see if anything exciting happens. Can you square x minus 3? And don't tell me it's x squared minus 9, because it's not. X minus 3 squared means x minus 3 times x minus 3. Foil it out. When you foil it out and simplify, you're going to get, well, you tell me, what do you get when you take x minus 3 and square it?
X squared minus 6x plus 2.
So is the first term squared twice this product plus that last term? All right, then I still have to multiply all of that by 2. I'm going to erase the stuff next to it and work this way. Send the 2 through the parentheses there. And I'll have 2x squared minus 12x plus 18. X squared minus 12x plus 18. Then I got the minus 18 out here. Turn up those 18s at each other out. And I can see why I'm getting 0 over 0. Both the numerator and the denominator have a common factor of x. So I'm going to factor it out and then cancel it. That'll leave me a 2x right there. Take that x out and it leaves me a 12. And we can cancel it and take the limit of what's left. As x goes to 0, 2x minus 12 does what? Negative 12. Negative 12 is our limit. So if you've got some operations that you can do, do them and see if that helps you to factor and cancel at a later stage and then find the limit. So the next one, let's see what kind of algebra you know here. Number 13. That's the eraser. Square root of x plus 6 minus 3 over x minus 3. X is going to 3, so I'm going to put a 3 here. 6 plus 3 gives me 9. Square root of 9 is 3. 3 minus 3 is 0 on top. 3 minus 3 is 0 on the bottom. Got to do more. Well, what can I do? What can I do is the more. I don't have that. I don't have factoring stuff to do. Okay. Can't take the square root of each term. Can't square that. I don't want to produce an equivalent fraction, and squaring a fraction doesn't make it equivalent. For instance, take a half and square it. Well, you get a fourth. A half and a fourth aren't equal to each other. When we're dealing with fractions, we can cancel common factors, or we can multiply by 1. So I want to multiply by 1. Anybody have any ideas what my 1's going to look like? Remember back when you first learned your algebra and pre-calculus, and if you had any kind of radical in the denominator, you were always told to rationalize the denominator. I'm going to rationalize the numerator. If there's just a single radical and no other terms like this 3 here, you just multiply top and bottom by that expression. But this changes things. If I've got a radical minus a number, or even a radical minus another radical, I multiply by the conjugate. Is that ringing any bells? The conjugate of this looks like that, but with the opposite sign in between, because we're going to use the fact that when you multiply two binomials of this form, that's the conjugate of the other one. And when you multiply this out, you'll get a squared minus BA plus AB. You get no middle term, then you get a minus B squared. So if any one of the first or last terms has a radical, this type of product will get rid of the radical. So I'm going to take that and I'm going to multiply by the square root of x plus 6 plus 3 on the top and the bottom. Yeah, multiplying by 1. I'm not going to multiply the bottom out because I'm multiplying by 1 with the hope that I find a common factor. So I'm going to keep the bottom in factored form. Now carefully multiply out the top. So I'll kind of just carefully with my blue pen. I take the square root of x plus 6, multiply it with the square root of x plus 6, and I get? That's right. Now if I distribute that to the second term, I get the square root of x plus 6 times a positive 3. I'm not going to write that down because looking ahead, my two inside terms multiplied together give me the square root of x plus 6 times a negative 3. So those two will add to 0. Finally, I have to multiply the two last terms together. A negative 3 times a positive 3 gives me a minus 9. And I can keep adding on top. X plus 6 minus 9 simplifies to x minus 3. Shabam, there's my common factor. I cancel the common factor. That leaves a 1 up here, right? X minus 3 over x minus 3 is the same as saying 1. And now I take the limit with what's left. Now I don't have 0 over 0 because I don't even have a 0 on top. I got a 1 on top. On the bottom, we're putting 3 where the x is. So 3 plus 6 gives me a 9 under the square root sign. Square root of 9 is 3. 3 plus 3 is 6. My limit is 1/6. Okay. So there's all kinds of algebra we can do when we have polynomial or polynomial type things. We are, though, going to encounter trig type things. So I'm going to give you two special trig limits. One we've already looked at. That one I did by crunching numbers, the sine of x over x. We said that as x goes to 0, the sine of x divided by x did what? What did we get as the limit? 1. Here's our next special limit. We got time to derive it. What's the cosine of 0? Cosine of 0? Cosine of 0 is 1. So this has the indeterminate form of 0 over 0. I'm going to show you what this limit is using that idea. I'm going to manipulate this expression so that I can find my common factor. I'm going to take this and multiply by the conjugate. Because I have a Pythagorean identity. I know that sine squared plus cosine squared of any angle is always 1. Well, I don't have a cosine squared. And remember, when calculating limits, if I want to generate a new fraction, I can't square my fraction. I can only multiply my fraction by 1. So if I want to introduce a square in here, I'm going to multiply this by the conjugate. So I'm going to take that expression there, and I'm going to multiply top and bottom. Stay down, you crazy little camera. by 1 plus the cosine of x over 1 plus the cosine of x. Again, I'm going to leave the bottom factor, but I'm going to multiply the top out. When I multiply the top out, using the FOIL method, first, outside, inside, last. First times first gives me 1. The 2 insides together give me a minus cosine x. The 2 outsides give me a plus cosine x. So those add each other out. And now the 2 lasts multiplied together give me a minus cosine squared of x. So cosine times cosine is cosine squared. We usually just put the squared right there. So when you see that, that means cosine of x is squared. And then I have this and that. Well, I don't have a common factor, but I have this identity in there. Sine squared plus cosine squared is 1. What is 1 minus cosine squared going to be equal to? Yeah, 1 minus cosine squared is sine squared. So I'm going to replace the numerator with sine squared of x. And then I have x and 1 plus the cosine of x. Well, it still has the form of 0 over 0. If you take the sine of 0, you get 0. 0 squared is 0. And that gives me a 0. So I still haven't gotten very far. But I have this limit in there. I'm going to factor it out and put it in the front. I'm going to write sine squared of x as the sine of x times the sine of x. I'm going to group one of these sines of x's here. I'm going to group the other one here. So I'm just kind of factoring. But now remember that if I have a limit of a product, I can write that as the product of the limits. I can take the limit of the first term, multiply it by the limit of the second term. The limit of the first term is my special limit. That's 1. When I go over here, I get sine of 0 over 1 plus the cosine of 0. Cosine of 0 is 1. So I get 1 times 0 over 2, which is 1 times 0, and that's 0. So save you some steps and just learn this one. There are 2 special trig limits. Sine of x over x as x goes to 0 is 1. 1 minus cosine of x over x as x goes to 0 is 0. If you know those 2, then we can manipulate other trig expressions to help us find those limits. And that's all the time I got for this week. So I've gotten you most of the way through section 2.2. Got probably another half dozen examples I'd like to show you. So if you want to start working on that homework set, go for it. But don't get discouraged if you don't know how to do every one of them, because I'm going to do more examples of this on our first Monday of the semester. All right, you guys have a great weekend. Shut this off unless you guys at home have any questions. Better at this camera thing though, huh? All right, we need to shut the camera off so folks can get out of here. Just do that.